Starting now. Cool. So welcome everyone. Thank you so much for showing up and joining today's CSML seminar talk, which is kindly sponsored by DeepMind. As you can see, we have the great pleasure of having Jakob Foerster here, who is one of the key figures in the field of multi-agent reinforcement learning. Jakob received his SciFar AI chair in 2019 and is starting as an assistant professor at the University of Toronto and the Vector Institute in this academic year. During his PhD at the University of Oxford, he helped bring deep multi-agent reinforcement learning to the forefront of been working as a research scientist at Facebook AI Research and is a co-author of multiple very popular papers such as counterfactual multi-agent policy gradients, learning to communicate with deep multi-agent RL, stabilizing experience replay for deep multi-agent RL, and many more. Today, he will talk more about his recent line of research of zero-shot coordination. And I'm really looking forward to today's talk. So without further ado, please welcome Jakob.
Great. Thank you so much for the very warm introduction. It's my great honor and pleasure to be here. Today, I talk about all of my unpopular work, so get ready. Joking aside, I think this line of work, zero-shot human-eye coordination in Hanabi and Rich Rider, is, I think, an important area. It's a very new area, and in the next hour or so, I'd like to convince you that this work perhaps one day also might be popular. So let's get started. What is the big picture? The big picture is we have to move away from self-play to finding policies that can cooperate and coordinate with other humans, with other robots and with humans. And I think that's a completely new field in some sense. Throughout this talk, I would like to make this as interactive as possible. So please ask questions. A lot of things will be confusing. And if something is confusing to you, others will also be confused. So please feel free either send the message in the chat or just interrupt me. Just jump in if something is unclear. I will try and answer as much as I can during the talk, and whatever isn't answered during the talk, we can get back to it at the end of the talk. So here's the broad outline of the talk. We'll start out by introducing human-eye coordination and theory of mind. And then in the first part, I'll talk about zero-shot coordination and our method, other play, that is an initial step in that direction. And then part two, I will talk about our more recent paper, Rich Rider, which is all about finding diverse solutions of problem settings, but also can be used to address zero-shot coordination. So in the last 20, 30 years or so, and more recently, we've seen artificial intelligence systems beat humans at a lot of games. It doesn't matter whether you think about Go, chess, Dota, or even poker. In all of these competitive games, AI systems now beat the best human players. But there's something that these games have in common. They're all two-player zero-sum. What that means is they're fully adversarial. And most of them actually are two-player zero-sum, which means there's only two parties playing together. And this begs a question. This is clearly great progress, but is this progress really what we want as a community? Is it really our goal to humiliate as many humans as we can by beating them at games that they have practiced their entire lives? Is human sadness really the goal of us as a research community? And I like to claim, perhaps controversially, perhaps not, that this is not our goal, that we want AI systems that can help and support humans, that we want AI agents that can work in teams with humans, that can cooperate, communicate, and coordinate. And unfortunately, the skills required for the latter task are completely different from those required by the first task. And we indeed have big question marks about how we even frame this first question. So we have to move away from two-player zero-sum, and we have to move towards this thing shown on the right-hand side. But what is this on the right-hand side? Well, clearly, we can define it as a multi-agent problem because we at least have the human and the AI agent. Furthermore, it's fully cooperative because my goal as the agent is to support the human. So only the human reward function is relevant. So it's one function for the entire team. And more importantly, commonly part of the world will be unknown to the AI agent. It doesn't matter whether you think about the human reward function, commonly that's not exactly specified, or for example, this robot can't see behind it. So this is a fully cooperative, partially observable system. Remember those words. And also, we can't do self-play, because clearly I can't agree with a human on an exact action for every state of the world. I will never, as an AI agent, be able to completely write the human's brain to be compatible with my actions. So there's always an element of zero-shot coordination that I will try and make this concept a bit more clear in a couple of slides. And what all of this requires is something called theory of mind. To illustrate that concept, imagine that you're cycling down the road in London and you see a person next to a bus stop raise their hand. Immediately, you know that there must be a bus behind you, because you ask yourself, why would that person raise their hand? It must be because they're signaling to a bus to stop. Therefore, there's a bus. And this ability of humans to interpret actions of others and act interpretable when being observed by others is what I refer to as theory of mind. And it's a crucial factor when agents are trying to communicate and cooperate and coordinate. But I think more broadly speaking, we are at the very beginning of a journey of trying to understand the fundamental principles required for coordination rather than for adversarial settings. And I hope that maybe in a few years' time, there's going to be a book written that's called the Principia Coordinationem, that's going to really capture all of our fundamental understandings of what it takes to coordinate in complex settings. Obvious question is, how can we make progress on this agenda? And I suggest that we use reinforcement learning as the underlying framework. So in reinforcement learning, we have an agent and a world. The agent obtains observations O and rewards R from the environment and takes actions U. Upon receiving the action, the environment transitions to a new state S prime that's sampled from distribution conditioned on the Markov state. But the environment itself, while the state is transitioning, the environment itself, the transition functions, are static. And this means that the agent can interact with this world over and over again to learn an optimal policy. And the goal here is to maximize the total expected return per episode. So just to discount the sum of rewards over time. Because I care about policies that can be applied in a world that's highly complex with a large state and action space, we'll be using deep neural networks, i.e. deep reinforcement learning, to parameterize the agent. So the agent obtains an observation that's processed by a deep neural network and puts out a distribution of actions or value functions. And this is indicated by the weights of the agent theta. Because we care about multi-agent learning, as I said, one agent isn't quite enough. So instead we have the red agent, the blue agent, and the green agent. And in general, they take their own actions, get their own observations, and obtain their own rewards. What makes this difficult is that the transition in the environment depends on the actions of all of the agents, not just one of them. However, remember, I'm looking at fully cooperative settings. So we don't need the general MAR framework. Instead, we can use the so-called decentralized partially observed Markov decision process, or DECPOM-DP. And the DECPOM-DP is exactly like the previous framework, with the difference that now all the reward functions for all agents are exactly the same. We have one team reward. Remember, thinking about human-AI coordination in the back of our heads, we're trying to help the human. We don't want the agent to pursue its own goals. We're going to help the human achieve their goals. And this is illustrated by the fact that all agents share one team reward. So, key question now, we have a framing that we can start with, reinforcement learning, multi-agent, or DECPOM-DPs, but we need a test bed. You know, at the end of the day, we want to build things that do something. So what's our test bed here? And as I said, all the games that are being used by the community are 2-player zero sum. They're not the best way of trying to cooperate with humans. Luckily, there is a relatively new card game called Hanabi. And we actually believe that this is one of the new frontiers for AI research. And the twist in Hanabi is that it's fully cooperative and partially observable. So it is a DECPOM-DP. And it's entirely focused on theory of mind. If you don't know Hanabi, which I expect many of you won't, let me give you a quick rundown. The big twist in Hanabi is that, as you can see in this picture, you don't see your own cards. So instead of playing the card game like this, I am playing the card game like that. So you, my teammate, can see the cards. I cannot see my own cards. Therefore, I have to reason over your intent for doing what you did in order to decide what to do. Let me make this a bit more specific. So here's a scene in Hanabi. We're just starting out the game. These are the hands of my partner, i.e. these are your cards that I can see, and these are my cards, I can't see them. These are the hint tokens. So you have 8 hint tokens to start out with. These provide grounded information, but they're not enough to play the game perfectly. So at this point, what you do is you point out a set. You pay a hint token to point out the cards that are ones. At the beginning of the game, all ones are playable because I'm trying to complete piles of cards, starting with a 1, ending with a 5. So that's what I do. I play a card. Obviously, at this point, I didn't know if the second one is playable because it could be the red one, in which case it's not playable. Now it's your turn again, and you tell me that this card is red. Now, a priori, this doesn't tell me anything about the world because this could be the red 3, the red 4, the red 5, could be another red 1, most likely, actually, statistically speaking. However, this is where theory of mind comes in. I can now reason over why would you have decided to tell me that this card is red? If you were a random agent trying random stuff, I wouldn't be able to do anything right now. But I know that you're a human that has theory of mind. So therefore, you know that I'll try and interpret your action as being meaningful. And that's what I do. I'll interpret this action as meaning I can play this card. This is probably the red 2. And in fact, that's what it is. And this kind of coordination works without prior agreements. If you just look at the rules of Hanabi and you have humans that sit down and play, they will do this kind of pointing to cards intuitively, and they will indeed reason over what other agents will understand. So I hope that gives you an illustration of the game. In short, it's all about reasoning over the intents of others. Now you point out there's a blue card, and again, I can now think over what that actually means, why I should do this. There's a big problem with this testbed as it's being used by the community, and that is that the default problem setting is self-play. So what we're doing normally in this testbed is that we train a team of agents, for example, the Argentinian team, together, and then we test them at test time in exactly the same constellation. And this is actually quite a good idea in two-player zero-sum settings where the Nash equilibria are interchangeable, where it doesn't matter what Nash equilibrium you pick, as long as you find one, you cannot lose at test time, you cannot be beaten. And in fact, you never have to reason over what the other agent, the other player, your opponents had for breakfast, what time of day it is, or who you're playing with. You're not going to lose if you're playing Nash equilibrium in two-player zero-sum. So to some extent, that is the best thing that you can do to make sure you're not losing. In contrast, in cooperative settings, those policies we've learned at training time only perform well within that specific team of AI agents they are trained with. So it's a huge difference between fully cooperative settings and two-player zero-sum settings. And I can illustrate this to you by looking at the best state-of-the-art self-play policies in Hanabi, which people have published quite a few papers now on self-play in Hanabi. And what you find is that if you train 11 different agents from exactly the same method in Hanabi and play them against each other or with each other in teams, you get this interesting cross-play matrix where the diagonal entries are perfect scores, essentially 24-point-something points. But on the off-diagonal, most of these agents get near 0 points. And that makes a lot of sense because they learn extremely cryptic conventions. So for example, the self-play agents learn to hint red or yellow to mean that the newest card should be played. And they learn to hint white or blue to say that the last card should be discarded, right? These conventions are extremely efficient, but they're very, very different from human conventions. And clearly, if you use those arbitrary codes, you're not going to be able to coordinate with a random stranger at test time because they might use completely arbitrary codes. And the result of all of this is that the self-play score on the diagonal is around 24 points, but the cross-play score on the off-diagonal, when we match two different agents, is around 3 points. And clearly, if I can't coordinate with an independently trained copy of myself, how can I expect to coordinate with a human, right? That seems very, very unlikely. So how do we move beyond this? This is where zero-shot coordination comes in, right? This is a framework where instead of training one team, we train two teams, the Brazilian team and the Argentinian team. But crucially, they are separated by a barrier during the training process. They cannot exchange any information. And the goal of zero-shot coordination is to find training strategies that allow these two different teams to play well together at testing in a single game after training is done. And you can think of this as being that the coaches can agree on a training strategy before training starts. And the question is, what should the strategy be, right? Now, this seems very easy, but the challenge is that unlike most machine learning problems, we're not allowed to evaluate the thing we care about, this cross-play performance, during training. We can only look at it once at the end of training. So we can tell easily that we failed to find good policies, but it's less obvious how you can find good policies that achieve this. We've taken an initial step in this direction with our paper called Other Play for Zero-Shot Coordination that was published at ICML in 2020 with a set of fantastic collaborators. So here's a sort of more formal definition. Again, we're assuming that independent AI designers have to construct agents for ex ante unknown DECPOM DPs without being able to coordinate on those specific DECPOM DPs, but they can coordinate on a training strategy. And the question is, what should that training strategy be so that you maximize the expected payout when their agents get matched in crossplay in the real world? You can think of, for example, maybe Waymo and Tesla at some point should be able to agree on certain things in the world. So let's illustrate this, why this is hard and different from self-play. So here's a little coordination problem where you have a lever game that's being played. And the goal is that you coordinate with a random stranger by choosing one of the 10 levers shown on the left. And if the two of you pick the same lever, you get the reward that's showing next to it. So if you pick this lever, you get 1.0. That lever, you get 1.0. Here, you get 0.9. But if you pick different levers, the reward is 0. Crucially, you have a single attempt with that random stranger. And this task description, so everything you're seeing here, is common knowledge. So my question to all of you is, I said it's going to be interactive, so let's start with that. What do you do in the situation? What do you play? Okay, someone has sent an answer here. I have a number of answers here. So we get 0.9 from a few people. And there's one answer, which is, don't you just more or less necessarily lose? Well, it'd be kind of a sad promising to give you if you were always losing, right? So no, you don't always lose. And in fact, 0.9 is what you can play because that is a unique answer here, right? And obviously a self-play agent would never do this, right? Self-play agents would just coordinate in one of these, and that shows you what the difference between self-play and zero-shot coordination. If I didn't give you this task description where I said you can train an exact team of agents that has to do well only with each other, you should play the 1.0, and we'll get to that. So let's go through the reasoning process here, right? So I think as a human, what we do is we basically replace this random stranger with a sort of imaginary twin in our imagination. And we imagine that this imaginary twin goes through exactly the same reasoning process as ourselves. So first step, let's pick an arbitrary 1.0 lever, me and my imaginary twin. I play that through in my head, and I pick that lever, my imaginary twin picks this lever, and we didn't coordinate. That's too bad. So let's go through the rest of the strategies. What else could I do? We could pick the 0.9 lever. We both go through the same process again, and we end up picking the same 0.9 lever, and suddenly we have coordinated, right? And there's a question about the uniqueness of 0.9. I think this little example shows it to you, right? If you break symmetries arbitrarily, then you can't expect to coordinate with a random stranger. But how can we generalize this idea of uniqueness and of symmetries? Well, the key idea are symmetries, in fact. So what are symmetries? Symmetries are mappings that leave this DECPOM DP unchanged. So if you think about the DECPOM DP as being a big tree, where you have states and observations and actions in transition in this tree, that tree structure itself actually is unchanged under these symmetry operators. So we call them phi, and they come from the entire set of all possible symmetries that are applicable to the DECPOM DP. And crucially, the transition probability is going from S prime given S and A is the same as going from the permuted version phi of S prime given phi of S and phi of A. So you can take the entire DECPOM DP tree, you can apply those symmetries, and you get the same tree. That's the definition of it. And because we have those operators, we can also apply them to the policies, because this phi of pi is nothing but the same policy pi that acts on a permuted action space and permuted trajectory here. So this is extremely abstract. So let me try and make this a little bit more explicit by giving an intuition. So imagine you have a world where you have a robot that's in the top right corner, and there's a goal in the middle, there's an X and Y axis, and the robot can move up, down, left, right. So clearly, if I invert the X axis, that's a symmetry, right? But there's a catch. If I just invert the X axis and put the bottom, put the robot, if I invert the Y axis and I put the robot to the bottom right corner, at this point, taking the green action, moving upwards, moves me towards the goal. But if I'm at the top right corner, taking the green action moves me away from the goal. And what that shows you is, if I want to make the green action equivalent, given where the robot is, I have to switch out not just the position, i.e. reflect the robot from the top right to the bottom right, but also permute the actions, i.e. switch out the green and the yellow action. Does that make sense? And that's where the symmetry operators have to act both on the state space and the action space. It's not enough to just act on the state space. But indeed, if I do this, then I get to a point where wherever I put this robot, the same color action has an equivalent meaning in that new position. Are there any questions on this? Okay, so if there are no questions, next question is, how do we use those symmetries? Right? So we have symmetries in the world. Symmetries leave the deck completely unchanged. What that obviously means is that if I apply a symmetry to a joint policy, I get the same reward under that equivalent policy, because I get from a policy to an equivalent policy. But how can I use this to learn better coordination policies, zero-shot policies? And that's what we do with other play. So in particular, in self-play, we can arbitrarily choose both sides of the team, pi1 and pi2. And we just maximize the expected return as a function of pi1 and pi2. In contrast, under other play, we're requiring that we cannot break symmetries arbitrarily. So what we're doing here is I can only specify pi2 up to the equivalence class. And that's equivalent to saying my imaginary twin can only follow the same kind of reasoning, cannot pick the exact same policy. So in particular, if I think pi2 is a great policy to play, then all the equivalent policies, phi of pi2, must be equally likely picked by my teammate. And because I'm sampling this phi from all possible symmetries, I'm actually playing against an expected policy from the entire pool of equivalent policies to pi2. And what this means is that this other play objective actually maximizes, it doesn't find the best performing policy, it finds the best performing equivalence class of policies. And that's shown in this little proof here. There's a question here, why not infimum instead of expectation? Well, you could, if you were risk averse, you could change this, right? You could try and maximize your minimum performance. But I think it's much more intuitive actually that you try and maximize the average performance in the equivalence class, right? And that's what's shown here. So it doesn't actually, by just permuting the second policy, you're really maximizing the expected return of the entire equivalence class because you can push around these permutation operators. They end up forming a group. The expectation is taken with respect to the entire symmetry class. So here are all the possible symmetry operators, and you sample randomly from those operators and apply them every episode. That's what the expectation is taken over. Great question. Thank you, Alex. Right. So this is what other play does. Other play tries to find the optimal equivalence class of policies. Because if I think pi2 is a great policy, clearly phi of pi2 is equivalent to pi2, has to have the same probability of being played. Okay. Oh, this is uniform. This is just a uniform distribution on the symmetry group, on all the permutations. And the nice thing is that other play can be implemented on top of any deep parallel algorithm once you know the symmetries. Okay. Any more questions? Great question so far. So what does this look like? This might still look a little bit abstract. As a picture, it just means nothing but this. We still train two policies. We don't do crossplay. We don't do mixing between the two different teams. We train the Brazilian team and the Argentinian team. But instead of being trained with the second half of itself, it's always trained with a differently permuted version of itself, or symmetry disturbed version of itself. So you can think of this as asymmetric domain randomization. Both the Brazilian team and the Argentinian team at training time independently. And then at test time, we test them in crossplay again, like before. Just to illustrate, this file is sampled randomly every episode. I've made a little animation that might be confusing or not, but let's pretend that up, down, left, right are symmetric. Then basically at training, we would pick random permutations of these, or random inversions of these every episode for both of the teams, right? So, and the key thing is that they're not told. No one knows what the current permutation is that's being applied, right? So what are the symmetries? What are the symmetries in Hanabi? In Hanabi, basically, actually, there was one more question here. Yeah, okay, so there's a question here that is align your thinking, and then you take the max, the best strategy that will come up with together. Exactly, it's basically the best strategy class now, right? Before in Software, we can agree on exact strategy and exact policy, the two halves of the team. Here, we can only agree on the policy class up to an equivalence class, right? And I have to find the best equivalence class, basically. And in particular, in Hanabi, the symmetries are pretty obvious because they are just the arbitrary labels of the colors. You know, red, green, yellow, white, blue, they all have exactly the same role in the game Hanabi, right? So therefore, if I permute all of the colors, including the fireworks, the hands, and the actions, I get exactly the same game back, right? You can imagine if I show you this game and I tell you this card is red, this card is blue, this card is yellow, the game is exactly the same if we change all the labels of the colors. It doesn't change any of the payouts, doesn't change any of the dynamics. And what this means is that when we're doing other play in Hanabi, we will have the two players play in differently recolored versions of the game every episode. And importantly, the recoloring is drawn randomly every episode. And here's an example where you have a permutation that switches out white and yellow. And so in one view of the world from one player, in this episode, the first card is a yellow one. I can hint to the playable card of the other player by saying, your first card is yellow, the yellow two is playable. And then in this specific episode, with that permutation, now that's a yellow 5, it's no longer a yellow 1, but there's a white one here. And the first card is still playable. The semantics aren't changed. I can still hint to it by using color, by saying this first card is now white, because I'm acting with my symmetries on all of the states, action, and so on. So that's how we do it, other play in Hanabi. There's a question here which was, do you need to manually define the transformations? The transformation includes inductive bias about the game, right? So that is a great question. The first answer is, in principle, you don't have to manually define it. Remember that these are properties of the deck POM-DP. They're not made up. These are true things. Remember the definition of symmetry earlier where I said, here's the tree and you can apply these phi's and leave the entire tree unchanged. That's a graph isomorphism. So no, they're not made up. They're not inductive biases. These things are fundamental properties of the deck POM-DP. And remember, the deck POM-DP is common knowledge to all parties in zero-shot coordination. So in principle, all parties can compute the symmetries from the deck POM-DP. However, that happens to be a hard problem. So we don't have a good method for that yet. So currently in other play, we're assuming that symmetries are provided. But remember, they're not arbitrary. They are properties of the deck POM-DP. They're not inductive biases, they're properties. However, I don't like the fact that this all depends on symmetries. And in the second half, we're trying to get rid of symmetries to a great extent. But great question, thank you. So what does this actually do? So let's look at the results. So first of all, in the lever game, this does pretty much what you would expect or hope for. In particular, at training time, it looks like self-play is winning because self-play gets 1.0 points all the time. So the thing that everyone does in our community, doesn't matter whether it's emergent communication, you know, DECPOM DPs, partial observer system, self-play is 1.0 points. So here our method is actually losing because at self-play we get 0.9 points. However, then let's look at what happens when you deploy your robots in the real world and they encounter other robots they have to coordinate with. Suddenly self-play gets 0.11 points in expectation, while other play gets 0.9 points still, because other play learned to play this variant here. Right? And other play obviously had to do this because that's the only way that it could find a policy that's robust to arbitrary symmetry breaking. So what does it do in Hanabi? First, for a start, if we look at bots playing with each other, we see that this increases the crossplay score by around 13 points for vanilla self-play method. And then if we further regularize the self-play method by adding auxiliary tasks, we still increase the crossplay score by 4 points. So this is the crossplay score now, 22 points when we add other play and auxiliary tasks. Now this is nice, but remember my claim was something else. My claim was this would be a step towards human AI coordination. I really haven't shown you that, but that's shown here. So here we took our other play bot and our self-play bot, and we made it play with humans that are self-described expert Hanabi players. And these humans played a single game of Hanabi with these bots. And what we show is the performance on a given deck of cards, because in Hanabi, the exact deck changes how well you can do on this game. And what you can see is, so for example, for this deck of cards, the other play bot obtained 18 points and the self-play bot obtained 3 points. And indeed, in all of these set cases, the other play bot did much, much better than the self-play bot. And in expectation, the other play bot obtained around 16 points and the self-play bot obtained around, you can take the average here, around 6 points. Right. So what this shows you is that other play can learn human compatible policies without requiring human data, right? And to me, all of this is an indicator that we've discovered the very first principle of coordination. Principle number 1, those shall not choose a policy from a set of equivalent but mutually incompatible joint policies. I think this is true about coordination. I think there's a lot more principles to uncover, but I also think that we have an extremely long way to go. So for a start, currently our RL agents cannot first understand the problem and then try to solve it, right? Because while we're doing reinforcement learning, we're settling on a solution while learning about the problem space. And that's an issue in zero-shot coordination because the zero-shot coordination policy needs to consider the topology of solutions. So we need new methods for that. The next question is how can we adapt on the fly, right? Because humans are really, really good at interpreting intent and then acting in a way that is interpretable and understandable. And what that means is humans can adapt to a broad range of different policies, good Hanabi players, on the fly. And we really don't understand how this can be done using learning agents in a general way. Again, I'm looking at the fundamental principles. I'm not trying to understand, this for a specific game, but I'm trying to understand the underlying principles for coordination. And this was asked before, what if you don't know the symmetries, right? So you could try and compute them from the DECPOM DP, but humans don't really explicitly compute them. They have a more intuitive understanding of those. And can we find a method that gets rid of this requirement of having the symmetries already given? And that's what we'll do in the second half of the presentation. We'll talk about Rich Rider. It will look extremely unrelated, but we will come back to this idea of zero-shot coordination, I promise you. So this paper was published at NeurIPS in 2020. And the big question is, how can we find diverse solutions? The answer is follow the eigenvectors of the hashing. The underlying intuition here is that when a measure becomes a target, it ceases to be a good measure. So remember our crossplay objective. If I was to optimize for it directly by optimizing my agent, by definition, I no longer evaluate the true objective. I make this objective meaningless. Just like my generalization objective, when I want to generalize out of distribution in supervised learning, I can't optimize for the holdout set. Otherwise, it's no longer a real holdout set. So for background, let's think about how we actually normally optimize the loss function as a community. For the last 20 years, we've basically done gradient descent, SGD. We just follow the gradient locally. And this has a lot of advantages because it's really cheap to do and it locally reduces the loss and it has a great empirical track record. However, we don't learn anything about what kind of solution was found using SGD. And SGD has a strong intrinsic bias towards easy solutions, which are typically those ones that have high curvature when steep solutions basically early on. And the question we ask is, how can we find a diversity of different types of solutions? And our answer is that we should follow the eigenvectors of the Hessian. So here's a saddle, a cost surface, and there's the first eigenvector, steepest direction. And here's the second eigenvector. What are those? They are nothing but the eigenvectors of the Hessian. So they satisfy the eigenvector equation shown here. So this is just the Hessian, the matrix of second order derivatives. And we just say that H times E is lambda E. Right. Now, importantly, H is a function of theta, and that means that each eigenvector and eigenvalue also is an implicit function of theta through the eigenvector equation. And what this means is that we can now ask what happens when we follow eigenvectors, in particular those with negative curvature starting from a saddle. So we're starting at a saddle, we have zero gradient, and follow this eigenvector EI, we get to this updated parameter point theta t plus 1, and we recompute the smooth continuation of that same eigenvector, right? So we're assuming everything is smooth, which means the eigenvector hasn't changed too much, and we can recompute it, the updated version here. Then we follow the updated version and get to some new place in parameter space. The question is, how much did we change the loss when we went to theta t plus 2? And the answer is that it's just the inner product between the parameter update and the gradient, the green vector, at the previous location. But what is that gradient? Well, remember the Taylor expansion of the gradient uses the Hessian, but this was an eigenvector. So by calculating the first order approximation, we just get minus alpha, the learning rate, times lambda I EI. And this means that the inner product between these two vectors is nothing but lambda times alpha squared times the inner product between the eigenvectors. And what this means is that as long as these eigenvectors are changing slowly or smoothly, we are reducing the loss by in any direction, in any eigenvector that has a negative eigenvalue. And that means that instead of having one direction, like in SGD, the gradient, we now have an orthogonal set of loss-reducing directions when starting at a saddle. Second question is, where do we start our optimization process? And here we introduce here we close the circle to symmetries. We go back to these ideas phi. So we have these symmetries phi now applied to theta that leave the loss function unchanged. So you can think of this as, for example, the permutations of a deep neural network commonly leaves the entire loss unchanged. And what we'd like to accomplish is that we start at a saddle that is invariant under all of these permutations. So up here it says for all theta, it's a symmetry if the loss is unchanged under the operator phi for all theta. In contrast, the maximally invariant saddle is a place in parameter space that has a low gradient norm, and for all phi, for all symmetries, leaves the weights unchanged, the parameters unchanged. This is basically a place that doesn't break any symmetries yet that exist in the loss landscape. And the reason is that if we do so, then equivalent solutions will have repeated eigenvalues, which lets us identify the presence of equivalent solutions, which we'll get back to. Obviously, if this required us to know the symmetries, that would be bad news, because then we have to know the symmetries of the problem setting once again. But at least in reinforcement learning, we can find the MIS by simply maximizing the entropy and minimizing the gradient norm. And because when you maximize the entropy, you will put the same weight on equivalent solutions, this ends up finding the maximally invariant saddle, which means we can find the MIS without having access to the symmetries of the problem a priori. So what does Richrider do? Richrider puts all of this together, and it basically starts out at this MIS, and then branches out to follow each of the ridges, the eigenvectors of the Hessian, in both the positive and negative direction. We always update the ridge locally and follow it, the updated version, until we get to a point where we cannot reduce the loss anymore. And here we branch. So we repeat the branching process. Crucially, when we're doing so, we use this fingerprint to keep track of the eigenvectors that were followed so far, right? So we have this notion that we know exactly how this solution was produced because we know we followed the first eigenvector. And here we followed the first eigenvector twice in a row. And when we're done with the training process, all these leaves of the tree are our solutions. And they, as I said, they come indexed with metadata. Right? Obviously, this is expensive, so we're estimating the Hessian. We also have to reevaluate the full spectrum of the Hessian at every time step. But in the paper, we have an approximate version of Rich Rider that only uses Hessian vector products and uses an an iterative procedure for updating the Rich every time step. And then we have many branches, but at least we can throw out equivalent branches by using the symmetries and using repeated eigenvalues to group these different solutions. So what does this actually do in a little toy problem? So here's a cost surface where you're trying to get to the loss reducing region. So the steepest loss is at the dark blue region outside the picture. You're trying to get there, you're starting in the middle. What does SGD do? SGD actually ends up always falling down the cliff here. It always ends up falling in the steepest curvature direction. So we end up in these local optima at bottom right and top left. Those are the empty circles. If you do ridge riding for the first vectors, first ridges, you end up in exactly the same places. Steepest ridges end up in the same local optima. However, the second ridge, E1, actually curves around this loss surface, goes around this local maximum, and ends up in the minimum loss region at minus infinity, right? And the orange ridge on the other side also curves around. Here we branch because we ran out of progress, and then curve around to the loss reducing region, right? Are there any questions on any of this? If not, let me close the circle to get back to the idea of zero-shot coordination. So how do we actually use this in zero-shot coordination? We now use exactly the same problem setting as before, but we've made it a little bit harder. Now there's a 0.6 solution and two 0.8 solutions. And the question is, how can we use Rich Rider? Well, our main insight was that symmetries lead to repeated eigenvalues. So if you have n different ways of solving the same problem, equivalent solutions, then you will have repeated eigenvalues at the maximum invariant saddle at the MIS. And because the ordering of the ridges corresponds to the ordering of the eigenvalues, repeated eigenvalues lead to inconsistent orderings during different runs. In contrast, if you have a unique eigenvalue, then you can coordinate reliably. By the way, quick question: what would you play in this game? What answer do you play? Great. So we have two different. Okay. I think by now people get the idea. So basically 0.6 in expectation gives you 0.6. If you pick 0.8 in expectation, you get 0.4 because there's two of them. You'd have to break the symmetries arbitrarily. And the 1.0 has 7 options. So you get 0.13. Great. And the question is, how can Rich Rider do this? Rich Rider actually ends up learning exactly the 0.6 solution. How does it do it? We run the Rich Rider procedure n number of times, and we keep track of the solutions indexed by the eigenvector that we followed. And that's shown here. So on each of these, you can see one run of Rich Rider. And in the plot, you see what policy was played. So if I play in my first run, if I follow the first ridge, I end up playing the 0.6 lever. So option lever number 1. And in contrast, and this is actually a reliable option. So in every different run, my first ridge produces exactly the same solution, which is the 0.6 solution. In contrast, the 1.0 solutions, which are the levers 4 to 10 here, they are inconsistent across my different runs. So in every different run, I have a different permutation of these ridges, of these solutions. And what that means is I can now run Rich Rider n different times, and I can imagine we can just coordinate on the ridge we followed, right? And what that means is we can calculate the crossplay score. If I pick the first ridge and you also pick the first ridge, what's our expected return? Obviously, for the first one, that's 0.6. So that's the solution we'll end up choosing because we just pick the ridge that has the highest expected crossplay score when you and me both pick it, but optimized independently. Any questions? So crucially, Rich Rider can actually learn the zero-shot coordination solution without requiring access to the symmetries, because we can find the MIS without knowing the symmetries, and we can then, from the MIS, run Rich Rider to find the ridge with the highest expected crossplay score. And by definition, Everyone is going to find that same rich during training, and then we both play that policy, our part of that policy at test time. Rich Rider also has applications. So this is how we discovered Rich Rider. It was trying to solve these kind of problems and exploiting symmetries in the product landscape. But it has applications in very different domains. So for example, we can use it to find diversity of solutions in reinforcement learning. So here's a little tree example where we have a shortcut solution. You have to move left or right, and plus is positive reward, minus is negative reward. And if you do independent learning, you'll typically find these shortcut solutions that are easy to find, but they're harder to find solutions down the tree. And with Rich Rider, we can really find a lot more of the solution. So if you run Rich Rider, you find around 100% of the solutions for a small tree and a lot of them for deeper tree, but doing just gradient descent or using random vectors instead of the ridges doesn't find those solutions. We also did some ablation studies here where we checked what happens if you don't follow ridges, but you follow fixed eigenvectors, or you follow random vectors in a positive direction. And basically we outperform random directions, but it didn't really matter in this tree that you used the ridges, that you followed the ridges. You could have used fixed ridges. And then we also looked at supervised learning using approximate Rich Rider, this iterative process. And here we could actually train an MLP, two-layer MLP with 128 units using the approximate Rich Rider algorithm, and we get around 89% accuracy in MNIST. I mean, obviously not state of the art, but at least this method can train deep neural networks. What was interesting here, though, is that we really got an indicator that Rich Rider does learn diversity. If you follow different ridges, you find that the early ridges correspond to classifying the digit classes 0 and 1, but later ridges, so less deep curvature directions, correspond to first classifying the digit classes 2 and 3, and then very flat ridges correspond to first learning to classify the digit 8. This is the accuracy shown here on the y-axis. So there's true diversity in these solutions being learned early on, according to different ridges being chosen by the algorithm. We also did an ablation here where we asked what happens if you don't follow the ridges around as they curve, but you follow a fixed eigenvector. And you can see that the best performance is actually significantly different. If you follow fixed eigenvectors, you don't exceed the performance of a linear neural network, of a linear classifier. But if you do Rich Rider, you get 89% accuracy, as I said. Interestingly, we could also extend Rich Rider to out of distribution generalization. So in particular, we looked at this color MNIST data set that has spurious labels. And we asked the question, if you require two different players based on different training sets to find consistent ridges, consistent eigenvalues, can we then try and find the causal solution? And the answer is yes. Some of the details are in the paper. So in particular, Rich Rider is closer to the IRM, state-of-the-art causal solution than it is to the standard SGD on the standard loss functions. So what did we do in Rich Rider? Basically, we did sort of like a search process ourselves. Rich Rider turns optimization into search, and we did that same thing with the paper. We first asked about diversity in TableauL and in MNIST. Then we generalized this to out of distribution color MNIST, to zero-shot coordination. We laid some of the theoretical foundations. But I think all of this is very, very early days for this research direction. So I hope in the future we can solve a lot more problems, find a lot more solutions to a lot of the problems, and maybe one day we'll find all the solutions to all of the problems. And if we're really smart about it, we won't even need all of the GPUs. So with that, let me come to a quick summary of the talk. What did we do today? First of all, I introduced the zero-shot coordination framework as a new frontier for machine learning research. If you're looking at cooperative settings in multi-agent learning, do not look at self-play. Self-play is almost always the wrong answer. And also, if you're not looking at cooperative self-play, at cooperative settings in multi-agent learning, then what are you doing, right? Can we please stop trying to make humans sad about being bad at playing games? I think everyone got the message now. Let's stop with that. We're done. Let's move on and try and do something that's actually good for humans. And crucially, zero-shot coordination is a step towards understanding the fundamental principles of coordination, which are radically different from those in other problem settings. Both fully cooperative self-play and obviously two-player zero-sum do not have any of those challenges that we need to address crucially if we want to build systems that can work with humans and other AI agents. Other play is a small step in that direction. So it addresses zero-shot coordination when the symmetries are known a priori. I shouldn't say it addresses zero-shot coordination, it addresses part of zero-shot coordination. As you saw, there was still a large gap between the human AI coordination performance and the bot performance, so 22 points versus 15 points. So there are a lot more things to figure out, as I showed in the middle of the talk with my little summary slide then. And other play does learn more human compatible policies. In the second half, we made a large jump to something that looks superficially unrelated to Rich Rider, which is following eigenvectors of the Hessian to learn diverse policies that come with metadata about what type of policy they are through the index of the eigenvector. And in Rich Rider, the symmetries of the underlying problem lead to repeated eigenvalues. We can exploit this property to learn zero-shot coordination solutions without requiring prior access to the symmetries. And it also establishes this underlying connection between out-of-distribution generalization and zero-shot coordination, which perhaps wasn't obvious. And I think all of this is connected to the fact that there are objectives that we're not allowed to evaluate directly during training, but we do want to optimize them. And Rich Rider lets you do this kind of thing. There's a lot of exciting work to do. So I invite everyone to be part of that journey. I think we're at the very early stages of this. And a lot of the code is open sourced on my homepage, jakobfoerster.com. With that, I'd like to thank you all for listening and open the floor to discussion if anyone has more questions. Thank you.
Maybe I'll start with a question.